Well, hello, welcome back to Engineering 201 Electrical Fundamentals, and I want to talk about experiment number 2 today. That's what we're going to be working on. So without further ado, let's turn our attention to that, talk about what we need to know to do that experiment, and then actually do the experiment and get the data, and then I will be able to send you on your way to do the analysis and whatnot. So let me change views on you here. And we'll do like we did the last time, talk a little bit about the circuits and some of the things that we hopefully will learn from each circuit, and the do's and don'ts for each circuit before we head to actually building this. So we have here experiment number 2. There's actually 3 circuits for experiment number 2. The first test circuit is a very simple series circuit. So we have 3 resistors that are in series. One thing that we'll do is we'll unhook the power supply here, and then we can measure the resistance across each one of these. If we were to leave this power supply hooked up, we would end up getting the equivalent resistance. So remember from last time, whenever we measure the resistors, we need to take care to make sure that we get the resistance of the individual resistor and not the total resistance of the whole thing. We'll also make sure that we measure the resistance of each element with the power off. That's going to be important. So that's that. Let me then look at some calculations. Whenever you think about coming to lab, you probably want to have some idea of what these values are. What should V1 be when we measure it, to make sure that we're not just totally out in left field? What should V2 be? What should V3 be? And the way we can calculate those, make sure I'm on screen here, sorry about that. Again, finding V1, V2, and V3, the way we do that is we do it by finding the current I. So if I were to total up this resistance, R1 plus R2 plus R3, because they're in series, and I divide the voltage by that, so there's the voltage, the source voltage, divided by R1 plus R2 plus R3, that gives me the current I. We know that current goes through each of these resistors, so then it's a simple matter using Ohm's law that V1 would be equal to I times R1, V2 would be equal to I times R2, and V3 is equal to I times R3. So those are our 3 voltages, V1, V2, and V3. And of course, one of our tasks in this circuit is to make sure that V1 plus V2 plus V3 does add up to be Vs. Now, it probably won't be perfect. If we were to analyze this mathematically, it'd be perfect. But to add up our data from the circuit, it may not be perfect because of experimental errors and whatnot. So that's circuit 1, the first part of the circuit. Let's move on to circuit number 2. No, sorry about that, not quite 2 yet. One thing, and this is probably fairly obvious, maybe that's why I was going to jump over it, is measuring the voltage last time. And this is probably something important to consider now because we're going to measure current for the first time, and we want to make sure that we do that right. So if I'm measuring voltage, it's really just as simple as measuring it across something. We put one probe here, we put one probe there. With the circuit energized, we will be able to measure the voltage. So in this instance, if our meter is set up correctly, we're going to be measuring the voltage V2. We'll do the same procedure for V1 and V3, and likewise for Vs. So we measure the voltage across. So you always want to think about the voltage across something. It's the current through the voltage across. So we did that last week very successfully, and I just wanted to reiterate that because current is going to be quite a bit different. Well, now, see if I can do this. Let's move on to the second circuit. The second circuit looks like this, circuit number 2, where we have parallel resistance. We have R1 in parallel with R2 and parallel with R3, and they're driven by a voltage source there. And what we're going to do is we're going to try and find I1, I2, and I3, and likewise I4, and hopefully that we'll be able to demonstrate Kirchhoff's law with that. Well, let's look at some of the details on this. So if I look at this circuit here, drawn out, pretty much the same thing that you saw before, we know then with Kirchhoff's law that I1 plus I2 plus I3 should equal I4. Okay, this current going in here, I4, has to divide up to I1, I2, and I3. So this statement is a statement of Kirchhoff's current law. Now, if we were to analyze this theoretically and mathematically, this would actually certainly be equal to. When we look at our lab data, it's probably not going to be quite equal to that. Again, we could have some inaccuracy in our measurements. How do we come up with the calculated values for this? If we wanted to calculate these values beforehand to make sure that we're measuring them correctly, that's pretty straightforward. Using Ohm's law, we can say that current's equal to voltage times divided by resistance. If I go back up here and look at the circuit, we see that the voltage across here, the voltage right across there, voltage across there is the same as the voltage across there, it's the same as the voltage across there, same as the voltage across there. So the voltage at this point here with respect to that point there is the same for all of those. So really when we look at I1, we could say that it's Vs divided by R1. Does that make sense? Yes, it's this voltage here divided by that resistor. Likewise, I2 is going to be the voltage Vs, that's the voltage across there, divided by R2, and so forth. There we go. I1 is Vs over R1, I2 is Vs over R2, and I3 is Vs over R3. And that's how we get those. And then, of course, if you wanted to calculate I4, you would use Kirchhoff's current law. Well, measuring, that's calculating. If we decide to measure those currents, we have to really remember when we talk about a current versus a voltage, remember the voltage was across something, the current is through something. So if I want to measure I3, for instance, I'm going to have to physically break the circuit and have this current then go through my meter. And it's an amp meter at that point. So whatever current I have going here, the circuit is broken. It can't continue here. It has to go through this amp meter and back here. Likewise, if I wanted to measure I2, I would break this, put the meter in there, and I'd be measuring I2. If I want to measure I4, I have to break this so that every bit of current goes through this meter and on its way. Now there's other ways to measure current. You can put a resistance in there and measure the voltage across the resistor like we did last week. You can have a clamp meter that uses inductive principles to measure that. But by far the most economical and the most accurate way for measuring these types of currents that we're going to be dealing with is actually to have the current go through the meter. So think of voltage again as across something. We measure across, current is through. We have to open the circuit, put the meter in, then we turn the circuit on, and that current flows through that meter, and we can observe that. Now, if it's an analog meter, and I brought one of those in, we have to be kind of careful. If we turn it on and the meter goes into the negative range, tries to hit the basement, go to the negative range, we'll know we've hooked this up backwards, and we'll have to change these leads. So that's how we measure current. We have to measure the current going through. So it has to go through our meter. And I think the last one, I'll back up and look at this circuit here. So circuit number 3, and you should have access to this in PDF form, so if it's a little hard to see on the video, you should be able to see it in the file. We're going to use a potentiometer, and we're going to use all 3 legs of the potentiometer this time. 1 leg, 2 leg, and that'll be the 3rd leg. We've got a couple other resistors, and by changing the setting on this potentiometer, we'll be able to change the voltage across this R3, which is going to certainly affect IX and power and things like that. So we'll get to study that. So that's what we're up to. What this looks like when we actually build it is something like this. I'll put my potentiometer in here with this, excuse me, R1 going into the middle leg of the potentiometer, and then the 2 outside legs of the potentiometer being across this R3. The voltage across R3 is going to be V0. Well, what we're going to need to measure on this is we're going to need to measure R3. That's a constant. This is just a set value, fixed value of resistance, so that should be a constant number. And then we will measure V0. So we'll put this potentiometer in 10 settings, and we will measure the voltage there. And this is actually quite a bit easier than last week. I don't have to take this in and out measuring the resistance here, because I really don't care what the resistance is. I just want to change it over 10 settings. So I'll probably dial it over here, take one reading of V0, I'll bring it around here, take the other reading of V0, and then I can just divide this up into 10 settings, and I will have 10 readings of V0. And the reason that I only need V0 and the fixed value of R3 is what I'm going to be looking for is IX. Well, IX is, of course, V0 divided by R3. You can see that here. IX, that current here, just by Ohm's law, I'm just going to take this V0 and divide by R3. And then if I start to want to get the power, I know that power is equal to V squared over R, or in this particular case, V0 squared over R3. And power is also equal to I squared R, or again, in this case, IX squared times R3. Now, the only thing that we have to be very careful of here is units, because we'll probably have volts and ohms or k ohms. So if we have k ohms, we have to be careful with that. If we have current in milliamps, we're going to have milliamps squared, and then R3 and k ohms. So when you get down to this part, you might do well to switch to base units. Measure everything in volts, ohms, and amps. Might be a smart thing to do so you don't have a units problem. Or you can use the millis and killas, and as long as you take careful account of the units and what you might need to do. So that is circuit number 3. I think what the procedure, we're going to connect the circuit shown in figure 1. That's that series arrangement, measure V1, V2, V3, and hopefully we've calculated that beforehand. We're going to connect the circuit shown in figure 2. That's the parallel arrangement, and measure the branch currents I1 through I4. And then finally, as I just was describing, circuit number 3, we'll connect the circuit shown in figure 3, vary the potentiometer over its entire range, take readings of V0 for at least 10 different settings of the potentiometer. So calculate the power dissipated in R3 using the measured values of R3 and V0. So we'll look at the particular questions that we need to answer on the question sheet when we get done taking the data, but I think this will suffice for now. So let's turn our attention to that circuit. So here is my circuit, and it's a game of compromise here in terms of trying to get a good view and whatnot. But I have essentially off screen here, I have the power source, and it's coming in here. This is the positive lead, and that is the negative lead. So I've just kind of got a bus bar, so to speak, coming down here, that this row of holes here is going to be the positive, whatever I tune it to, and this is going to be the negative. So I come over here and I have the connection to the negative, and I can come over here and I can make the connection to the positive, not there, right there's the positive, sorry. So this would be the positive side. It's going to go through that resistor, through that resistor, through that resistor, back to the negative side. Now, as I mentioned already, if I want to measure the resistance here, I cannot have this hooked up, because essentially between the positive and negative, this source appears fairly low resistance, and I will end up getting the resistance of the whole thing. So I'm going to go ahead and open this up, just put it in an arbitrary hole that's not connected to anything, so it's not flopping around. And I'm going to bring my ohm meter in here and measure the resistance. You'll notice that well, I guess it's not in view, but trust me, I've got the circuit off. We've got to have the circuit off when we measure the resistance. So I can come in here now, because this is unhooked. and I can measure R1. Let me see if I turn the light on there, if you get a little better view. So 0.98 k ohms. So I'll jot that down. 0.98 k ohms. And what was that supposed to be? I believe it was 1 k ohm was what was called out. Then this one, and again, there's no polarity with resistance. I could switch these leads from like that to putting the red down here. I don't have to worry about it like when I measure other things. So 1.96. Why don't I say 1.97? 1.97. 1.97 k ohms, and it was calling out 2 k ohms. And we talked last time about the tolerances on these. It's gold, so it's 5%. So we're well within that. And this last one right here is 3.31 k ohms. And I believe it was called out as a 3.3, so it's nice and nicely on there. So now what I'm going to do is get ready to hook this up. So I've got this hooked into the ground. This one needs to go into the positive over here. And I've got this dialed up at 5 volts, so we should be okay. The other circuits that are on here at the same time, I've got them unhooked, so they're not going to be affecting anything. I won't be overloading these circuits and whatnot. We're just going to be looking at this one, this series circuit, this circuit number 1. So let me turn it on. There we go, no smoke. And let me, now I'm going to start to measure voltage here. So I need to put this at voltage. The straight line over the top, that's DC. The squiggly line, that'll be AC. We'll spend a long time next term talking about that. What is this really measuring in terms of peak or RMS or that? But we've got the DC, so we don't have to worry about that. And I can put this probe right there. And maybe this one up here, that should be the source voltage. And it looks like I got right at 6. So VS is nicely at 6. I did better on that than I thought. 6.0 volts. I have to admit that was a little luck. When I set it a few minutes ago, it was 6.02. So now I want to go around here and I'm going to measure from here to here. So this will be the voltage across resistor 1 that we call V1, and we have 0.939. So I'll just go ahead and record those, and we'll round things off and whatnot when we process the data. So 0.939. And the next one is V2. Let's see, the resistor is twice the value, so we'd expect twice the voltage, 1.887. So I'll say 1.89. And finally, this last one right here, I've got 3.16. Okay, so let me turn the power off and look at our data for a moment. So we've got R1, R2, and R3. It's good that we know those. Now, what if you, in your calculations, used 1K and 2K? That's fine, but if in your calculations you come back and use these values, you're going to get a little better number. So it's good to have these. If one of them was way off, maybe we grabbed the wrong resistor or it's out of tolerance, that's going to tell us why we're getting funny results. So it's good that we've got those. Then when I look at the voltage, let's see if I take this, it's about 2, and that's about 1. I've got what, about 3 and another 3. It looks like it, well, I guess this isn't about 2. I'm off by a little bit. This is a little less than 2. This is pretty close to 1. It's a little over 3. You add this to this to this. Looks like it's going to come up pretty close to that 6. So I think our data is just glancing at it, looks good. I actually ran the numbers beforehand, and I'm pretty happy with these. I'm not going to, share those numbers with you necessarily, because I want you to run the numbers beforehand to calculate V1, V2, V3. That's good practice calculating, and you'll be able to judge whether we're in the ballpark on this or not. So that's circuit number 1. I've got that data. Like I did last week, I'll tidy it up, put it into Excel, and get it ready for you. Clean up some of the significant figures and whatnot. This was, remember, 6.00. I think everything's pretty good other than that. Well, let's move on to circuit number 2. And remember, that was, with too many papers here shuffling around, circuit number 2 was this parallel arrangement. So let's make that happen. So I've got this off. I want to unhook this circuit. So I'll disconnect that so that I don't, if I use a larger voltage, I think I'm going to use 9 volts on this. Probably wouldn't be a problem, but I don't want to overload this. So this is my circuit 2. We see these 3 resistors that are here in parallel. I could hook them up over here if I wanted to. I'll put that into the positive, and then that's the negative, and we have the 3 resistors. And I've put them here in order that you see them. I'll get my hand out of the way, try and move these a little bit. There we go. So we've got resistor 1, so current I1 is going through that. Resistor 2, current I2 is going through that. And resistor 3, current I3 is going through that. And I'm going to move this just a little bit so we're a little more centered up on here. Okay. So I'd like to measure the resistance here. So I'll unhook this like I did last time, and put my meter up here. I'll turn the light on. I think that makes it a little easier for you to see. Power's off. I've got it on resistance. If I come here and say, oh yeah, I'm a good electrical student, I'm going to measure the resistance, we're probably not going to get anywhere close, 214 ohms, because that's the equivalent resistance of those 3. So we're not getting what we want. We didn't learn our lesson last week well, and we tried to measure the resistance of one resistor, but we got the equivalent resistance of all of them. So let me do better here. Let me take this resistor, the R1, and I'm going to move it and put it in a different slot down here, like that. So now it's not connected. So I'll put the leads across here, and I now have 0.64 k ohms. 0.465. And I think we were looking at 470 ohms for that. So that's good. I like that. Let me go ahead and put that back in so I don't lose track of where it is. That methodology seemed to work nicely. Let's do the same with this. So I'll pull it out, and I will measure the resistance across there. And I have 663 k ohms. 663.663 k ohms. I was expecting 680, so we're not too bad. Let me double check that. .663662, yeah, that's fine. So we'll put that one back in. We'll pull this one out because I want to measure its resistance, the resistance of it only. So this is R3, and we have 0.978. 0.97, well, let's just call it 0.98. And that was supposed to be 1 k ohm, so it looks pretty good. Okay. So we'll put this back in here. I'll make this connection now to positive. So you can see our positive bus here, it's going to come over to here and then around here back to the negative. So between this point where all of these are plugged in and between that point, we're going to have the source voltage. And I need to adjust the source voltage now. So let me put this on volts. Let me put this across here. I want to put, this will be the positive side. This will be the negative side. And turn this on. And we had 6. That shouldn't surprise us. What are we looking for? I think we're looking for 9, aren't we? That's what we had to do. It's a little touchy. I think I'll leave it like that. 8.95. Yeah, that's good. 8.95. Maybe we can tinker with it a little more. Not too much of a good thing. Should have. .98. So we'll take that. 8.98. 8.98 volts, and we wanted 9 volts, so that's good. Okay, so this thing is on. It's presumably working. We'd like to start to measure the current. Okay, so I'm going to set up to do that. To do that, I'm going to turn off the power here, and I think I'll change my leads on this thing. Maybe I'll switch meters altogether. Okay, so I'm back, and if you look at these meters, there's usually a common, so I'm going to put a lead in there, and then volts, ohms, and a lot of the measurements we make is right there. That's where we've had it hooked up. But I want to go over here. I don't want to probably be in amps. I think the values are going to be small enough. This is another reason why you want to do pre-calculations, so that you know your what the value is going to be roughly. I think we're going to be in the milliamp range. Now these are fused. If I exceed it, it's going to blow the fuse. And actually in lab, we wouldn't use a meter like this because, yeah, blowing the fuse is nice so it doesn't ruin the meter, but the fuse is about $9 a pop. So it can get expensive fast. And I'll show you the meters that we use. They're analog. They're really robust. But this brings up a good point here. If I am unsure what the value is, I probably want to start as high as possible. I want to start in the amps range. Well, I'm pretty sure that I'm going to be in the milliamps, so I'm going to go in here in milliamps, not microamps. But if I was the least bit unsure, I'd want to put it up here in amps. Okay. And these leads I switched. They just have clips on the end to make them a little easier to use. So let me start with I1. I could just move this over here. I just need to put it in an unused spot. And I'll put my meter in here like that. Okay, and make sure I bring this clear over to milliamps. If I hit the orange button, it'll be AC. The default is DC. And we'll see if I did this right. So it looks like I have 19.3. 19.3. So let me jot that down. That's milliamps, 19.3 milliamps. So that's good. Now I need to, and what's going on here is the current that's going through this resistor is going through this meter. So this red lead here, right there, is the same red lead right there that's going into the meter. So this lead is the same as that one. It's going through this meter. It's going through that meter to the black lead and back over to here. Okay. So you're going to have to trust me. I don't have any funny business going on with these leads or anything. The red one's going into the red on the meter. The black's going into the black on the meter. And we've got 19 point, well, it was 3.6. Now it's 4.1. I'll stick with the 3.6 because we won't wait as long on the other ones. But we are getting what's going through that. Let me turn the power off. Disconnect this. Put this R1 back. Pull this R2 out. So I'm going to pull this middle one out. Put it over there. Hook this up. Okay, and whether I hook it to this one or that one, it really doesn't matter. You know, I always have students ask me, you know, can I hook it to either one? I said, well, let's say it's 10,000 volts and I give you a paper clip. Are you going to be more comfortable touching one or the other of those? So these are all at the same value there. They're all hooked together. I think I'm ready to go. We'll power up again. And it looks like we have 13.53. We'll call it 5.5. 13.55 milliamps. Good. So again, we've got the current that's going through this resistor is going through the meter and back down to there. Turn the power off. Put this resistor back. Take this last resistor, so this is R3. Put him over here in an unused one. Power up. And I have 9.16 milliamps. 9.16 milliamps. And I actually went ahead and did the calculations on these. I'll tell you, all those numbers are in the ballpark. I think they'll be good data for you. We got 19 and some change, 13 and some change, and 9 and some change. Some of you will add those up real fast and figure out what R4 is going to be. So let's do that. So I'll put this back together. I've powered off the circuit, obviously. Our resistors that are there. So I want to try and get this I4. That's going to be the total current going through all of these. Well, that would be the current that's going through this wire, right? I mean, I4 is going to be in here. I4 is likewise going to be in here. It goes through this, divides up, comes back together. So the current in here or the current in there would be I4. So let me pull this thing out. Make a connection here. Put that up there. And then I'll put this here. So the current for the whole thing is going through the meter and then back into there. Let's see how that goes. Now this should be higher. We're going to exceed the 400 milliamp range. That's what this is on the meter. It's listed on the meter right here, 400 milliamps. I think we'll be okay. So I have for I4 41.7, and I think we are pretty close with that. So that looks pretty good. Now, before I take another peek at the data and whatnot, I want to talk a little bit about that. We've been doing this with a digital meter, which probably, if you go out in industry, is going to be very, very common. Had we turned you loose in lab, we wouldn't have done this because we'd have had about half the fuses burnt out. If you overvalue it or put it across something like you're going to do voltage, you can easily burn out the fuse, which, good news, protects the meter, but you're still going to be buying the fuses, opening them up, putting them in here, and whatnot. So how do we do this? How would we do this? Well, let's remember this number, 41.9. And I'm just going to unhook the leads out of the meter. So I'll take these leads out right here and set them right here. Now, good thing I've turned this off, because I mean, this is the current. It's trying to flow from there to there, right? So good thing I've turned it off. Take this meter out of here. Put this meter in here. And we get a wood block. It's real high tech. Okay. So, and the range on this, there's the common. So we'll put the black into that. And then, should we start with the 25 milliamps, the 100, or the 50? Well, if we don't know, we always want to start with the highest. Okay? We always want to start with the highest. And then, if we don't get a very good scale, if it's way down on the meter, then we start to shift down. Well, I know that the value is going to be, well, maybe I'll leave it like this. In fact, maybe I'll really mix things up. Let's say that I get these backwards. Maybe I haven't hooked them up right on the circuit. Maybe I've got these two opposite. Let's see what it does. So I think you've got the meter there. Let me fire this thing up. You see that needle? Tries to jump down. Let me do it again. So I'm going to turn it on right there and watch the needle on that meter. Jumps down. Okay. So I've obviously got this backwards. Okay. So there it's on the 100 scale. Would I want to go to the 25? Well, no, I think we're measuring 41. That's way past the 25. In fact, that needle would hammer hard over to the right-hand side. So which scale are we on? Well, it's 100 is the maximum. So the top scale here is 25 maximum, and then the lower scale is 100 maximum. Well, that corresponds to what we have there, right? So I need to read these numbers that are on the upper lower side. Okay, so I need to read the 100 or the 80 or the 60 or the 40. So it looks like I'm 40 and some change. So these are, let's see, 40, 2, 4, 6, 8, 10. So it's 2. So it looks like I'm really close to 42, a little less than 42. So this isn't probably as easy to read as the digital, but it gives us good results, and it gives us the same results. I'm just shy of 42 milliamps. What do we say with the digital? 41.7. They don't get much better than that. Okay, so you can do good work with an analog gauge, and analog gauges are oftentimes very, very tough. Okay, these gauges were set up for student use, and really the worst thing you can do to this thing is drop it. Okay, so if you're ever in a lab and have to use an analog gauge, start out at the highest value. If the needle seems like it's trying to go down, you're going to have to probably switch polarity. But you can do good work with analog gauges. We'll see this in a couple more experiments too. So we turn the power back off. Take this out of here before I break it. I think I can pull these leads out. I'll unhook this from the power source and get ready to go to circuit number 3. So I need to move this up quite a bit for circuit 3. Okay, so this was circuit number 2. So down here is circuit number 3, and circuit number 3 is kind of hard to see. What we're going to do here is we need to kind of turn this guy, and it looks like we've got the positive going through R1. So I took the page here, I turned it, I've got the positive going through R1, and then that's my potentiometer, and then across the potentiometer is R3. Okay? So let's see if we can make that work. Before I get too carried away on that, let's look at the data just real quick from the previous circuit. I just recorded those, and again, I'll tidy this up, put it into Excel, so you've got it. There'll be no excuse. Oh, is that a 9 or an 8 or whatnot? And then again, we see the I1, I2, I3. You add those up, I think we get pretty close to that. So I am fairly pleased with that. So that's our data for 2. So let's really the data that I need here. I need to get the resistance of this resistor R1 and the resistance of that R3. So let me do that. Put my meter back up here. I switched meters again on you, so I'm back into the common and the volts and the ohms. Turn the light on. I want to measure resistance. So I want to take this resistor out here. Let me just plug it in over here and measure that. So that's let's just call that 9.8 k ohms. 9.8 k ohms. That's R3. And I believe we were expecting 10 k ohms, so we're in good shape on that. So what I'm going to do then is I'm going to take this and I'm going to put it back in here, and it's just really a little bit dreadful to see. But what I have is I have a potentiometer that's built into this. Remember last week I had one that was with wires. Well, good or bad, I've got one that's built in. It's a 10K potentiometer, and these sets of holes here are one of the outside leads. These sets of holes here are the other side of the outside leads, and then all of these holes in the middle connect you to that middle tap that moves around. Okay, so that's what I have going on. So if I look at the circuit, that R3 is across the outside. So what I'm going to do is just put that right back in here. Okay, that's R3. Let me pull R1 out. I think I can do that without, well, I'll just pull him out here. And we'll measure that resistance. Also, 4.64. 4.64. And that was k ohms, and we were expecting 4.7. So we're in good shape there. Let me double check that. Yeah. Okay. So I'll put this back in here and then try and justify the circuit to you piece by piece, because this is a little harder. Okay, so that one is your R1, that's your R3, and then your potentiometer is built in across those points there. So what I have here then, if I'm looking at the circuit, I'm going to hook this in to the positive side, and I have that hooked into the negative side. So let's look at this. I start out here at the positive side right there, and I go through this red wire into R1, so that's our R1, so these are connected. The R1 goes in here, which is the middle lead of that potentiometer. Then across the potentiometer, I have placed R3 right there. That's across the potentiometer. Okay, you've got R3. And then I also need to tie this whole thing to ground. So this point R3, the one side of the potentiometer, and I need to hook that there. So that's this wire here, this yellow wire, that's hooking the potentiometer and R3 all to ground. Okay, so I need to get this going with VS is 5 volts. Let's tune that up. So turn this down because it was at 9. Put this up here. Okay, so I've got it on volts. And I need to measure from there to there. So it looks like a 6, and I wanted 5, right? So I probably should have gone clear down, very low. But there we are. So we've got 4.6. If we were going for 5, that's pretty good. So I got 4.97. I'm going to call that close enough to 5. 4.97. So I'll record that. I don't know that we'll need that, but it's better to end up with too much data than too little data. So now what we want to do is I want to twist this knob. This is the knob on the potentiometer. I'm going to twist it to the one extreme, and I'm going to measure the voltage across V3, which is 2.516. Let's call it 2.52. So that's 2.52. And so that's V naught. And then if I turn this clear the other way, that'll be the other extreme. Let's see what that is. Looks like we got about 0 there. Okay. So I got 0 volts. And then just for completeness, I'll go clear back. Measure this here. 2.52. So that appears to be the maximum. 0 appears to be the minimum. Then it would be just a matter, and I'm not going to make you watch me do this, turning this, basically dividing this up into tenths, turn it a tenth, measure it, turn it another tenth, measure it, and get our data that way. Okay? So I'll go ahead and turn this off. So looking at the data, I've got R1, I've got R3. R3 is going to be very important with this. This is going to be an important number. This VS isn't of particular importance, but this range is very important. I'll go ahead and when I give you the data, I will fill in the values between here, but it's going to go from 0 to 2.52 volts. And the reason that you only need this number and this number is, as we had back in the calculation section, right here. So that was our circuit. certainly easier to see here than it is right there, but that's life. You open up an appliance or something, the circuit can be pretty hard to figure out what's going on. But with practice, we can do this. So the big data that we wanted was R3, we've got that, and then we measured that V0, because if I do the calculations, I can get the current. That's the current here is the current through R3. I get that by taking V0 divided by R3, and then my power right there. So R3 is in k ohms, so I'm going to have to be very careful of that. I might want to convert to base units, and then I should be able to come up with the power there. And the reason that I want the power is because that's my task. And bear with me if you will. I need to find the question sheet here. So what are we going to do with all of this? Well, here's your question sheet. Okay, this is what we want to do. I'll send this to you in a Word document so you can fill it out, put graphs in here and whatnot. This is what you're turning in. This is your deliverable. This is what needs to be just excellent. So explaining the differences between the measured and computed values in procedure 1. That's the voltages around that series circuit, V1, V2, V3. You'll calculate them and then compare those to the measured values. Okay, are they the same? If they're not the same, why do you have the difference? Well, then let's not blame the resistance in the wires. For this type of circuit, we have nice clean connections, properly sized wires. The resistance in those wires is virtually negligible. Okay, we could probably a lot more easily blame this. Okay, our meter. Although this is a good meter, it's still going to have some errors. If we look at the analog meter over here in part number 2, the scale, there's a lot of uncertainty in that scale. So we could talk about that too. Also, remember we measured all of the resistors. This is data for 3, but it'll work. That was supposed to be 10K. Well, we were only 9.8K. So that is going to change things a little bit. So those are all places where your measured may differ from your computed. Show your data from procedure 1, that was that series circuit, obeys Kirchhoff's voltage law. Do voltage 1 plus 2 plus 3 add up to be the source voltage? Show that your data from procedure 2, circuit 2, that is the parallel one. Okay, that's the parallel circuit, obeys Kirchhoff's current law. Does I1 plus I2 plus I3 add up to be I4? And I think we already said that was pretty close. Now again, if it's not exact, where are the reasons for that? Okay. And finally, you've got your graph here using the data from procedure 3. That was circuit 3. Plot proper curves, so labeled axes, all of that stuff. Plot proper curves of power in R3 versus V0 and power in R3 versus IX. Put power on the vertical in both plots. So those should be interesting curves. Make sure you sign this. Make sure it's very professional, very neat, and you are done with the lab. Email it back to me, and you've got it done. So hopefully, as we wrap up today, you've learned how to measure current. That's just one way of measuring current. Like I mentioned, there's other ways, and we'll explore some of those ways as we work through this for a year for the electricals. You've learned to measure current at least one way. Got more practice measuring resistance and measuring voltage, and got to see series circuits and parallel circuits and potentiometers in action. So I think this is a good lab to learn with. Well, if you have questions, shoot me an email. I would be happy to try and describe those and whatnot and try and answer those questions. Good luck with your lab, and take care until we see you next time.